We typically think of mass as a measure of physical stuff, how much matter is packed into an object. But in modern physics, mass is a geometric property. It is the invariant space-time length of a particle's four-momentum vector. This diagram tracks a particle's trajectory in a 3D Minkowski spacetime. The equation defines the relationship between total energy, momentum, and invariant mass. As the invariant mass variable decreases to zero, the momentum vector mathematically aligns with the edge of the light cone, reaching the universe's absolute speed limit, c. Currently, experiments place the upper limit for the photon's mass at less than 10 to the negative 18 electron volts. However, the mathematics of special relativity do not strictly require this value to be exactly zero. If the photon possessed even a trace of mass, light would simply travel slightly slower than the universe's ultimate speed of causality. We would merely decouple the speed of light from the absolute speed of information. Because relativity leaves the photon's mass as an open experimental boundary, we have to look toward quantum field theory for a rigid prohibition. While relativity is flexible, the Standard Model is not. Within the framework of quantum electrodynamics, the photon must be identically massless to maintain the theory's integrity. This creates a central tension. How does the Standard Model dynamically generate heavy masses for particles like the W and Z bosons, while strictly forbidding it for the photon? The answer lies in a mechanism where specific mass values determine whether the vacuum of space is a permanent state or a temporary one. By stepping through the electroweak Lagrangian, we can see why gauge symmetry forbids mass, and how spontaneous symmetry breaking provides a loophole, and how the resulting eigenvalues place our cosmos in a state of terminal metastability. This is the kinetic term for the photon field within the U1 QED Lagrangian. The electromagnetic field tensor, F mu nu, is defined by these derivatives. Its foundational requirement is invariance under local gauge transformations. A local gauge transformation alters the vector potential, A mu, by the derivative of a local phase, eta. When we apply this to the field tensor, the derivative terms cancel. The kinetic Lagrangian remains invariant, perfectly stable regardless of the local phase. But look at what happens if we attempt to add a standard Dirac mass term for the photon into this equation. We apply the exact same gauge transformation to this mass term to test its mathematical viability. The transformation fails. It produces extra, non-canceling terms that change the equation based on the local phase, destroying the symmetry. This failure establishes a fundamental rule. Any explicit mass term added to a gauge field inherently destroys local gauge symmetry. Because the universe obeys gauge symmetry, the mathematics requires all gauge bosons, including the photon, to have zero mass. This leaves us with a contradiction. If gauge symmetry forbids mass, why do the weak interactions W and Z bosons possess immense measurable masses? The solution is spontaneous symmetry breaking, triggered by a complex scalar field. This is the mathematical potential of that scalar field. Its shape is determined by the balance between these two terms. Because the mu squared parameter is positive, the state of minimum energy is no longer at zero. The potential takes the shape of a Mexican hat. The field settles into the trough of the potential. This value, the vacuum expectation value, is the non-zero ground state of the field. In the unitary gauge, we parameterize the field so that only the neutral component acquires this value, which mathematically removes unphysical Goldstone bosons from the theory. By settling into a specific point in the trough, the vacuum no longer respects the full original symmetry, allowing for the generation of mass. The actual masses of the gauge bosons emerge from the kinetic interactions of the scalar field through the covariant derivative. The squared covariant derivative tracks how the gauge fields couple to the vacuum state of the Higgs field. When we substitute the vacuum value into this derivative, we isolate the specific interactions between the gauge fields and the Higgs field. The expansion reveals newly generated quadratic terms. These function mathematically as the mass terms that were previously forbidden. The interactions of the W1 and W2 fields generate the specific mass of the charged W bosons. Similarly, the neutral W3 and B fields mix to generate the massive Z boson. But this mixing matrix leaves a critical remainder, one combination with an eigenvalue of exactly zero. This is the photon. This zero value exists because the specific vacuum state of the Higgs field is electrically neutral. it does not break the symmetry of electromagnetism. Because electromagnetism remains unbroken, the photon escapes the Higgs mechanism, remaining strictly massless while its sister bosons become heavy. The specific masses we have derived for these particles feed back into the structure of spacetime itself. Experiments at the LHC have measured and confirmed the exact mass eigenvalues for the Standard Model's heaviest particles. The Higgs potential is modified by quantum loop corrections from the particles it interacts with. Its self-interactions exert an upward pressure, attempting to steepen the potential. This is countered by fermion interactions, most notably from the top quark, exerting a violent downward pressure. The measured masses of the Higgs and the top quark create a delicate imbalance in this exchange. At high energy scales, the downward pressure of the top quark eventually overwhelms the Higgs self-coupling. The specific masses resulting from the Higgs mechanism determine the long-term stability of the vacuum we inhabit. Because the top quark dominates at high energies, the outer brim of the potential turns over and drops into negative territory. This indicates that our current vacuum state is merely a local minimum, a false vacuum. A much lower, true ground state exists beyond the barrier. We can map this risk on a phase diagram, comparing the mass of the Higgs to the mass of the top quark. The latest collider data places our universe narrowly but firmly inside the mas-stable region. This suggests that while our vacuum has survived for nearly 14 billion years, it is not a permanent configuration. Eventually, a quantum fluctuation could allow the vacuum to tunnel through the potential barrier. This would trigger a decay to the true vacuum, moving at the speed of light and instantly altering the laws of physics. The same gauge symmetry that requires the photon to be massless also demands a mass architecture that may eventually destabilize the universe, unless there is physics beyond the Standard Model that we have yet to discover.